A closed greenhouse in direct sunlight traps heat fast. Without ventilation, the air stagnates, humidity spikes, and the structure designed to protect plants bakes them. You can buy commercial automated vent systems to fix this, but they cost a premium. You can achieve the exact same automated airflow using discarded electronics. Look at this diagram. You only need 5 core pieces of hardware: a standard 12-volt PC cooling fan, a small solar panel paired with a 12-volt battery bank, an Arduino microcontroller, a DHT11 temperature sensor, and a relay module. If you can strip a wire and cut a square hole in plastic, you have all the physical skills required to put this together. Effective climate control comes down to reading the environment and turning on a fan. You don't need grid power or expensive kits to do that, just basic logic applied to scavenged parts. Step 1 takes place on the workbench. We need to prepare the salvaged computer fan to run on our new off-grid power source. Modern PC fans often have 3 or 4 wires for speed control and monitoring. We only care about the bare essentials here. Isolate the red power wire and the black ground wire, and ignore the rest. Before wiring any smart controls, we must verify the fan works with our power source. Test the fan directly against the 12-volt solar battery bank. Do not wire the fan directly to the raw solar panel itself, because the panel's output drops drastically the moment a cloud passes by. Relying on a battery buffer solves that fluctuation problem. A fully charged 12-volt battery ensures the fan spins at maximum speed whenever the system calls for cooling, regardless of the immediate shade outside. Now we set up the electronic controls. The main engineering challenge here is mixing different voltage levels safely. To do that, we use a relay. Think of a relay as a digital bouncer. It uses a small, low-voltage electronic signal to physically close a heavy-duty switch. As this diagram shows, our logic starts at the environment. We wire the temperature sensor into the Arduino's input pins, allowing the microcontroller to continuously read the current heat levels. When the temperature gets too high, the Arduino sends a low-voltage logic signal out to the relay's control pin. That signal closes the switch. This completes a separate heavy-duty circuit, routing 12-volt power from the battery through the relay and into the PC fan. You must keep these 2 power paths separated. If you accidentally crosswire the 12-volt battery power directly into the 5-volt Arduino pins, the microcontroller will burn out instantly. The relay isolates the low-voltage brain from the high-voltage muscle, allowing a tiny 5-volt chip to safely command a heavy 12-volt fan. With the hardware wired, we plug the Arduino into a computer to inject the automation rules. Before writing any logic, open your code editor and install the DHT sensor library. Without it, the software won't know how to translate the sensor's raw data into readable degrees, causing immediate compilation errors. Once the sensor is reading properly, we write the trigger condition. Look at this highlighted line of code. If temp is greater than 25 degrees Celsius, that dictates the exact threshold where the fan turns on. Now validate the code. Point a hairdryer at the sensor probe to drive up the heat, simulating a sweltering greenhouse on your workbench. Hearing the fan kick on from the hairdryer heat confirms the system works. Verifying the software logic indoors saves you the frustration of tearing apart a fully installed greenhouse setup over a single missing line of code. We take the working system outside. Heat rises, so find the highest point on your greenhouse exterior to mount the exhaust fan. Hold the PC fan up to the plastic wall and trace the inner square opening. Take a razor blade and slowly cut along that traced line. You want to avoid tearing the surrounding structural plastic, keeping the hole exactly the same size as the fan blades. Next, secure the fan housing directly to the wooden frame. It needs to sit perfectly flush against the wood. Any gaps will cause air leaks, drastically reducing the fan's ability to pull hot air out. Finally, route the power cable outside and mount the solar panel where it receives maximum southern sun exposure. The physical installation is entirely about maximizing efficiency. You pull the hottest air out the top while capturing the maximum solar energy outside. Greenhouses are hyper-humid environments. Leaving bare circuit boards exposed inside will guarantee a short circuit. To protect the brains, secure the Arduino and battery inside a sealed plastic project box, making sure to plug the entry points where the wires pass through. Look at this cross-section. The delicate Arduino is sealed safely inside, but the temperature sensor probe protrudes down through a rubber grommet. It has to stay exposed so it reads the actual greenhouse air, not the trapped, stagnant air inside the plastic box. If your project box requires ventilation holes, glue a fine mesh screen over them. Heat-seeking insects like ants and wasps will very quickly move into a warm electronic enclosure if they find an opening. Proper weatherproofing requires controlling condensation and locking out pests to guarantee the automation survives multiple seasons. With everything mounted and sealed, the setup sits dormant. The fan remains off, waiting for the environment to change. As the morning sun clears the tree line and strikes the panel, the interior greenhouse temperature begins a rapid climb. The sensor registers the heat crossing the 25-degree threshold. The relay clicks, and the exhaust fan instantly spins to life, pulling cool air over plants. You get precise, off-grid climate control. It operates exactly like commercial gear, but it relies on basic logic and scavenged parts.